Hello, welcome back. We have lots to cover today, so I'll get right into it. I want to talk a bit more about some of this regression modeling stuff, and hopefully we have a bit of time towards the end for you to practice more of this yourselves. I hope you brought a device and are ready to do that. Um, Hello.
Hi.
Um, I'm going to be covering especially a few tips and tricks from these sources. And if you look in the shared folder with all of the reading materials, you'll find these chapters that I handpicked for great content that you should look at for all of the content behind this lecture. Okay, and then there's a few more pointers to things you can read that I'm going to leave here in the deck that you can look at afterwards. So let's start with a small case study to warm up. Let's say you're studying the impact of advertisement through different channels on sales of whatever product you're advertising across 200 cities. So you have three channels through which you're advertising: TV, radio, and newspapers. Okay. X-axis is amount of advertisement through that channel. Y-axis is sales of the product. Okay. And there's 200 data points corresponding to the 200 cities that you've been running these ads in. Okay. So far, so good. Okay, good. So some things you might look at or want to answer. Is there a relationship between advertising budget and sales? One type of question you could ask. How strong is the relationship between advertising budget and sales? Which media contribute to sales? Do all of them do? Do some of them do? How accurately can we estimate the effect of each medium on sales? How accurately can we predict future sales? Maybe you're looking to make predictions about where to invest more in advertisements. Is the relationship linear or does it have a different shape? Is there synergy among the advertising media? Is there some sort of catalyst effect when you combine them, for example? So all of these are the kinds of questions that you might want to ask for variables you collect from some empirical study or from data more broadly. So for this, we use regression. We've already started talking about this. It's a very common way of modeling data and modeling these relationships. You're maybe familiar with linear regression, for example, something like y equals a x plus b, something like this. So you have a bunch of data point observations, and you're trying to estimate these coefficients, right? You're learning the coefficient from the observations, and you're using that to determine if there's a relationship. Of course, there's many possible models. For example, for this particular data set that I gave you, you can imagine, infinitely many lines to describe that data set. But some of these lines are better approximations of your data than others, right? All of these are approximations of your data, just like some are really bad approximations of your data. Okay? So presumably you're interested in a model that approximates your data well. So that's you obtain one by minimizing this error. So when you do this, what's left is called residuals. So we've estimated this regression line between this set of points. What's left for each of the points, right? The line that we've estimated does not go directly through the points, or maybe goes through some points, but in general does not go directly through the points. So there's some residual error that's left for each of the observations. Those are called residuals. If you look at the distribution of those, it should appear how? What does this look like?
Uniform distribution.
Random? Yes.
I say uniform distribution.
Okay. It should appear like a random cloud of noise. This is indicative of you having a good model to begin with, right? If it does not appear to be a random cloud of noise, your model is probably a wrong or whatever, insufficiently accurate approximation of your underlying trend in the data. Okay. So, okay, so there's this thing called, I don't know, least squares regression. You've maybe seen this before. You're sort of learning, you're estimating these coefficients by minimizing the sum of squared errors. How do you tell if your estimates are accurate? So, there's some true relationship, linear relationship between your observations. That would be the red line there. Let's say it's, 3x plus 2 is the real relationship between these observations. That's maybe the process that generated the data in the first place. You cannot observe this, right? That's unknown. That's why you estimate this from data in the first place. So, you estimate this based on the observations in a way that reduces this error. So you can think of this, you can think of all of these as, you can think of all of these least squares lines. Right, so if you draw a random sample from your observations, estimate one of these least square lines, keep doing that repeatedly, like draw another random sample, estimate another of these least square lines, and so forth. If you estimate all of these least squares lines by drawing random samples from your observations, the average of all of these estimated lines is pretty close to the true population regression line, is the idea. Okay. Okay, so natural question, how accurate is, right? So you could think of this, like how accurate are these coefficients? You could think of this by analogy to estimating the population mean of a random variable. So how accurate is the sample mean as an estimate of the true mean of that population? When you think about that, you think about standard errors and confidence intervals. So maybe you've learned about this before. For example, 95% confidence interval. It's the range of values such that with 95% probability, that range will contain the true value of the true mean of the population. Okay? So similarly, you can think about 95% confidence intervals or standard errors on these estimated coefficients, right? Because each of these regression lines is one of these least squares lines. You can compute them all by drawing different, samples and estimating different coefficients every time. So you can compute the standard errors on those coefficients. So this allows you to compute, standard errors and a confidence interval for those coefficients. So you could do something like, in this case, you could say that the slope estimate is, so that's beta 1 there, that's between 0.04 and 0.05, 95% of the time. Okay? Similarly for the intercept. Right, so, in the absence of any advertising, that's the intercept, right? The TV sales equals 0. In the absence of any advertising, sales will on average fall somewhere between 6.1 and 7.9 units of whatever product you're having. That's the value of the intercept. And it's, by the way, this is good practice to report the actual confidence intervals for these coefficients as opposed to just the coefficient itself. Gives you a better sense of range there. Because if your standard errors are super high, the confidence interval will be super wide. So if you report the confidence interval this way, the reader gets a much better sense of how accurate your estimate of this coefficient is. If you just report just the coefficient itself, I mean, yes, you should also separately report the standard errors in your paper, but if I'm just reading this, maybe I won't go and look for those, right? Unless you explicitly, name them or point them out or write them next to the, coefficient in your main body or whatever, right? So, it could be misleading if you just report the estimated coefficients. Good practice to report the actual confidence interval for the coefficients. And similarly, you can reason about the slope. So you know how to read these, right? For every unit increase in x, you get the beta increase in y. Okay. So here, because the x is very small, beta 1 is 0.04, 0.05. Because they're so small, I multiply all of this by 1,000. So instead of reasoning about every unit increase in advertisement, I reason about every $1,000 increase in advertisement. So just multiply everything by 1,000. Okay. So $1,000 increase in TV advertising, right? That's, one unit jump in the TV coefficient should give me beta 1 times 1,000. So that's about 42 to 53 units of the whatever product increase in sales. Okay? And it's good practice to report the actual confidence interval, because otherwise you would just say, it's, I don't know, somewhere in between those two, right? So this gives you a better sense of how wide the range is. Okay. I'll pause for a second. Anything surprising so far in this? Hopefully you've seen some of this before. Yeah, sure.
Two standard deviation is because we are zero Gaussian.
Yes. Yes. Okay. Okay, so now the key idea for empirical research is that standard errors can also be used to perform hypothesis tests on these coefficients. Okay? So essentially, you could test a null hypothesis so to test a null hypothesis that there's no relationship between x and y, okay, it suffices to test the value of these coefficients, or rather, whether the confidence interval crosses zero or not. Okay? I see sort of puzzled faces. Ask anything. So basically, right, so testing that null hypothesis is equivalent to testing whether the estimated coefficient is significantly different from zero or not. So if there's no relationship between x and y, right, because of the nature of this relationship, if there's no relationship between x and y, the value of this coefficient should be about zero. Because if there were a relationship between x and y, right, if you change x, you should expect y to change. That can only happen if the value of this coefficient is different from zero. If the value of the coefficient is zero, that means it does not matter what value x takes. It will have no impact on the value of y. Whether x is 100 or 100,000, if you multiply it by nothing, it will have no impact on the outcome variable here. Right? So that tells you there's no relationship between x and y. Yeah. Right. Otherwise, if it's different than zero, there is a linear relationship, right, with this shape. Yeah. Okay. So there's a test that gets automatically ran and or computed, and associated p-value for that test that gets automatically reported by all of your statistics software. And we've seen examples of this. We looked at the p-values for some of these regression tables together. For example, when we looked at the meter paper on Thursday, actually, no, was the Google paper had a nice regression table, I think. The meter paper did not. Is that right? Okay, something like this. We've seen some examples of these. They look something like this. So, if your p-values are small enough, you can conclude that these estimated coefficients are substantially different from zero, then you can conclude that there's a relationship between your X variable and the outcome.
Even if the coefficient is close to zero.
Yes, what matters is not the value of the coefficient, but rather whether the confidence interval crosses zero or not. So in fact, what you will see is, if you compute the confidence interval for these coefficients, so this thing minus 2 standard deviations, this thing plus 2 standard deviations, you'll see that one of those is on the left side of zero, the other one is on the right side of zero. When you cannot reject the null hypothesis.
Whenever p value is smaller than that one.
By construction. Yeah. Okay, here's another example. This is directly output from R. So you have a small data set there, X and Y, and we've estimated this model. So here we've estimated that Y equals about 0.5 times X plus 3. So if X is 0, the value of Y is about 3. And then otherwise, for every unit increase in X, you get about 0.5 increase in Y. So for example, going from X equals 0 to X equals 10 should give you about 5 units increase in Y. Okay. You also see the p-values for this t-test that gets computed that tell you whether or not these things are sufficiently different from zero. And you can also do that by computing the confidence intervals and standard errors like we just discussed. So in this case, this is a model that fits well. And you can see that it's sort of pretty clear that it's a model that fits well. Sort of approximates the observations pretty well. Yeah, this simple linear model approximates the observations pretty well. Okay, so let's make this a bit more realistic. How do we now extend our analysis to accommodate all predictors? We have only done this pairwise. We've looked at only one of these things in isolation. So for example, we could run 3 separate linear regressions for each of these variables, right? One for TV, one for radio, one for newspapers. The TV one is the one we just discussed. That's the one on the top. The one for radio is in the middle. The one for newspaper is at the bottom. How do you read these? Is there a relationship between radio ads and sales, and similarly between newspaper ads and sales?
Radio ads have a lot more impact in sales than newspapers.
Okay, yes, correct. Well, yeah, okay. We'll come back to a caveat there later, but yes, I agree with this.
I would think that maybe you're looking for similar beta values where it's like, oh, if they have the same slope, across like, okay, newspaper makes sales go up this fast, radio makes sales go up the same amount of fast.
I mean, that's what Teresa was saying, I think, also.
When you do that, you should put the intercepts to be safe when comparing the coefficients, right?
I'm asking something I think simpler. Is there a relationship at all here? Can we conclude that there's a relationship between radio ads and sales, and similarly between newspaper ads and sales? We've already concluded there is one between TV ads and sales.
Yes, for radio, not for newspaper.
Why?
This p-value is much.
It's below the cutoff, right? You normally cut at 0.05.
Yeah.
They're both statistically significant.
Then it is.
Yes? Do we agree with this? Right? All of these, if looked at pairwise, would show that there's a relationship between ads on each of these channels and sales. And they may have different slopes. Some of them are stronger. Okay, that's fair. All right, so now that's fine, but it's better still to throw everything together in one joint model, because this way you can account for the covariation between these. So that would look something like this, where you're estimating a joint model with all of these predictors at the same time, and you're estimating these different coefficients for each of them. So the beauty of this, as you probably know, is that when interpreting the beta coefficients, either one of the estimated beta coefficients, we can assume that all the other ones are held constant. And we've discussed an example of this, I don't know, a couple of lectures ago. There usually have 4 categorical variables. There was one example where we were puzzled by why the baseline category was whatever it was, and it was because it was chosen alphabetically in that case, right? So all of the other predictors are assumed to be held at their baseline values, okay? And these coefficients tell you how varying just the one changes the outcome independently of all the other ones. Okay, that's the beauty of this. The independently of all the other ones is the beauty of this, meaning holding them constant, fixed. Yeah.
Awesome. So like, how do we know what value to set for beta 2 if we're looking for beta 1?
Say that again.
So the way we are interpreting it is like how much changing beta 1 changes, how much changing the TV advertisement money changes the sales.
Assuming everything else is held constant.
Constant to what value?
Their default values.
Oh. So like for radio, it would be 1, for newspaper, it would be. Like,
So it depends on the. So usually when people interpret these, you set the other predictors or variables at their mean or medians. It's sort of a common interpretation, right? So you're saying, assuming everything is held fixed at their, median values, here's how much you can expect sales to go up for every unit increase in TV advertisement. It's typically sort of a.
Basically mean of what the radio and newspaper values.
That's commonly how you interpret these. The point is that it doesn't matter that it's held constant, right? That this is sort of independent of the shape, the slope is independent of the values of the other.
Okay.
Right. So your reason, the beta is just the slope. You're reasoning about the change in outcome, not about the actual absolute value of the outcome. If you want to reason about the absolute value of the outcome, which is often useful, then you have to instantiate the other variables.
Yes.
And commonly that's done at, for example, the means or the medians.
Yeah, and we are making an assumption that there is no interaction between these things.
As specified, the model does not account for any interaction between them. Yeah, that was a good question. Is this clear for everyone?
Can you repeat that once?
Say again.
Can you repeat that once? The summary of the.
Yeah. So the beta coefficients are the slope of the relationship. So how much the outcome changes, difference in outcome, not absolute value of outcome, how much the outcome changes for a unit increase in TV sales. Okay, not absolute value. So it does not matter for that kind of reasoning. It does not matter what the values of the other predictors are. It can be anything, right? Because the difference will be the same. But often you want to make descriptive claims about the absolute values of the outcome variables, right? So to do that, you need to instantiate all of the variables in the model. And I think common practice is to, for example, fix the other ones at their means or medians or something like that. Does that make sense? Now's the time. Yes? Okay, all right. Okay, so we like this framework, this multiple regression framework a lot, because remember the 3 ingredients for making a causal claim. temporal precedence, presence of association, measurable association, and being able to exclude plausible alternative explanations. So, of course, so presence of association, that's,
The first one is not even visible.
yes, because the first one you can ensure by design. It's not interesting, right? You can measure things in such a way. Well, it's visible on my screen. It says cause precedes the effects. But you knew this already because we've talked about this before.
You guys have talked about it before.
Point is that temporal precedence you can just ensure by design, so that's not interesting. The measure of correlation is this coefficient, right? That's a measure of the association between these variables. So that's great, right? You have one. So now, right, the third one, as always, it's tricky, but, should you have a good theory for what the mechanism is and what the confounding variables are, should you have that theory going into this, right? You could plug in to your multiple regression covariates to control for those alternative explanations. So I'm obviously cheating, right? If you're, I don't know, paying attention, because I'm just shifting the cost here, right? So the cost is, coming up with the theory in the first place, is figuring out what these plausible alternative explanations are. Okay? But should you have such strong theory that describes and explains what these alternative explanations are, then all you have to do is just plug them into a multiple regression, for example, to hold them fixed, control for them, and you're done, right? So you get a good, like, this by itself is purely correlational, but could be much stronger, right, in principle, if you have a strong theory that describes the mechanism, right? Because that theory would explain what the alternative explanations are, right? If there's only 3 possible explanations for your observed effect, if there's only 3 that are ever possible and you control for the other 2, you get a pretty good sense for the effect of the first one. Does that make sense? It's never this easy though, right? So like, arguing that you have controlled for all the plausible alternative explanations, that you've identified all the plausible alternative explanations, not controlled, identified for them, that's hard, right? You can do this maybe in an artificial toy example, but it's hard to do this in general. But should you be able to do this, right? So something like this gets you the kind of machinery that would allow you to make causal claims in principle. Okay, it's hardly ever, probably never, hardly ever sufficient, but it could in principle. I want you to connect the discussion we're having now to this discussion we had, I don't know when, about the role of theory and understanding the mechanism and alternative explanations and all of that. I want you to make this connection between these 2 parts of the class. Yeah.
From the numbers, how do you know the difference between the first case and the second case? So like, just looking at the coefficients, how do I know if the cause was related to the effect or if the cause preceded the effect?
The first thing you ensure by design, by how you measure and whatnot. You trust that the measurements are taken in such a way that this property is satisfied, is preserved. You have to ensure that by design. There cannot be any confusion about what came first. But for example, if you're the one that are running the ads, you know how much you've spent on ads, and then only later, afterwards, after you've spent the money on ads, do you measure sales, right, in your product, of your product. It's like you ensure this by design, ideally.
So far we have established correlation then, right? Not causation.
Well, I'm saying there's three things you need to satisfy to be able to make a causal claim.
Well, the third part is what's telling it's not just correlation, but causal.
Yes, the third part is always the hard part. And I'm saying, if you can argue that you have explored all the plausible alternative explanations. This framework, if you can name and measure all the plausible alternative explanations, then you can just include them in a framework like this, a multiple regression framework, as simple as this, right? And then you can have a pretty, credible estimate of the causal effect. In practice, this is never this easy, but just imagine this, ideal world where you can convincingly argue that you've identified and are able to measure, because if you are not able to measure, you cannot have these variables in your regression. You should be able to measure all of these plausible alternative explanations, have variables for them.
Am I saying this correctly? So once I have these coefficients, I know there is some sort of correlation, but after I've exhausted all possible alternatives, I can say it's a causation.
Yes, correct. So the correlation is what the individual beta coefficient gives you. And then the other, including all the other ones in the same regression, is what gives you this accounting for plausible alternatives.
Makes sense. But there's no way to prove that you have accounted for all possible alternatives.
Correct. Certainly not with this design.
I'm not really sure how to pose this question, but how would I remember when we first started talking about this thing, we saw those graphs of things that were correlated, but probably not causally related.
Yep.
How would that map to these three, or rather, how would we eliminate
Yeah,
that
great.
those things were causally related using this framework completely?
Excellent question. So they would show up, let's say, Nicolas Cage movies versus people who drown in a pool. Was that one of them? So, one of them is on the left-hand side, that's the outcome variable. People who drown in the pool is the response variable. The outcome variable, that's the thing on the left-hand side. Nicolas Cage movies is the thing instead of TV, right? So then you would get a strong correlation. You would get you would estimate a beta coefficient that describes this relationship very well. Okay? But you have not accounted or included in your model for any plausible alternative explanations. So there, I guess the heavy lifting has to be done at the level of the theory or the logical reasoning, right? I would ask you, what's the mechanism, right? What's the mechanism through which Nicolas Cage movies would cause people to drown in a pool? Right, so that'll be like my first level of inquiry, right? So you come to me with this, statistical correlation between the two, right? And then I would ask you, what's the mechanism, right? So you have to present me with a credible mechanism through which that thing can cause the other. You have to specify it, right? Articulate it. What is the mechanism? Is it that it's the same people that watch the movies that then, I don't know, throw themselves in a pool and drown? Is it that they're watching the movies while being in a pool on a, I don't know, like a floating thing, and I don't know, they accidentally drown while getting distracted? You have to articulate what the mechanism is, and it has to be credible. But if you can't do that, then I start poking holes at your theory. Your theory is about Nicolas Cage movies causing people to drown in a pool. But I start poking holes and I start arguing that maybe there's alternative explanations for this observed effect. Right? Maybe there's a coincidence, right? And there's some other third thing that you have not yet considered or measured or included in your model that accounts for that, observed, I don't know, outcome. So again, this is why I like mechanisms. So we talked, I think, a lot about how establishing a causal relationship between two variables is usually not sufficient for understanding the underlying mechanism. We talked a lot about this when we argued for the use of theory, right? So I don't know, I gave this example of scurvy and, lemons or whatever. The establishing the causal link happened much earlier than understanding the, I don't know, biological or whatever mechanism through which that thing, one thing was causing the other.
So basically, in that sentence, when you say plausible, it's basically the same thing, having a theory to back the thing up, right?
Right. And considering alternative explanations.
Because I was thinking the other way around. So if we found a good explanation for the number of people drowning, and we then came up with an alternative explanation that was the Nicolas Cage movies.
Yes.
I guess
But it has to be plausible. It's not
exactly,
enough
and
to
the
just be.
plausible part would be having an actual mechanism that explains that.
Yes.
Uh-huh.
Yeah. Like if you can articulate a convincing mechanism,
Mhm.
it becomes much more plausible.
Yeah.
At the level of logic, just pure logic, in a math sense. Can you derive one from the other? Like, there has to be a path.
Mm.
So, in the Google paper we read last Tuesday, they were, finding a even causal relationship, at least a correlation between AI use and productivity, right? But an alternative explanation for the productivity observed differences was that their samples were imbalanced, and just by chance, the ones that ended up being more productive had more experienced engineers because the samples were pretty small, right? So an alternative explanation for the observed differences in productivity is differences in experience. So not use of AI, which is your main hypothesized effect, but rather alternatively, differences in individual experience levels, right? And then they did actually test and found that there are differences in individual experience level. And in fact, they showed, I think, that the AI effect becomes statistically insignificant once you control for experience level. If you remember the discussion on Tuesday. Right, but both of these have plausible mechanisms, right? AI has a clearly plausible mechanism, right? You can hypothesize that AI will speed up development and why that is the case. And similarly, you can explain why individual experience with programming would explain differences in speed. Right? More experienced engineers can program faster or with fewer mistakes or whatever. Right? So you can explain clearly and very plausibly what the mechanisms are in both of these cases, right? Which makes them both very plausible. And similarly, you can imagine a third one, like Nick Cage movies, right? But then if you can articulate the mechanism through which Nick Cage movies can plausibly correlate with the outcome, then that doesn't quite meet the bar for inclusion in the analysis. So, by the way, I may have gone on this rant before. Like often, at least in the past, reviewers would complain, like, you've not considered confounding factors. Therefore, whatever, reject. And the reaction is, I mean, sure, but tell me what the plausible ones are. You can't just say you have not considered, all other variables that exist, right? That's not a good criticism, right? Tell me, name at least one, right? And articulate a plausible mechanism through which you could impact the outcome that I have not considered, right? Name it and articulate the mechanism, right? So that would be a valid criticism, right? But just saying, look, there's other things that you have not considered, even if you name them, you have not considered Nick Cage movies in your, analysis of the impact of AI, right? That's not a valid criticism because you have to also articulate what the plausible mechanism could be. right? I should not consider Nick Cage movies and any other nonsense just because I can, right? I should only consider it if it has a plausible path to the outcome, causal path to the outcome, right? So like, this is really important in sort of how you think about this. Okay, more on this? Okay. All right, so now let's look. Remember the three models that we had before when we separately regressed sales on each of these types of advertisement. Those are the three things on the left. The one on the top right is the joint model that we just estimated with all of them together. Okay. What do you notice?
Newspaper is no longer significant.
Newspaper is no longer, the coefficient for newspaper is no longer significant, meaning there is no longer evidence to claim a relationship between newspaper ad sales and product sales.
So if I were to do, let's say I did the first one and then the second one, and I see this difference, how would you kind of go about rationalizing it? Like, how would you comment on? Would you say, oh, initially when we just did newspaper versus sales, we found it to be correlated, but when we did all three of them together, what?
Yeah, so we were you here on Thursday?
Yeah.
We if you remember, we talked about the meter paper. One thing that I was sort of interesting about the meter paper and how it was written was that they had tested
Yes.
just this sort of bivariate relationship and then enumerated a bunch of plausible alternative explanations and went and tested them one by one or right, did some additional analysis for each of those. That's fine. I much prefer the style of the top right thing there, where if you are aware of these plausible alternative explanations, I mean, in this case, by design, you're aware of the fact that you are buying ads through three different media, right? So if you know this ahead of time, it's a little misleading to try to do this bivariately. You should just do this jointly, right, to begin with. So I would say don't do this at all, in this case. Just directly do the joint model where you have more robust evidence, right? Because this is misleading.
I mean, the only conclusion is that it's just an artifact of data that you see significant results with the newspaper coefficient.
It's an artifact of not controlling for covariates. So if that's what you mean by data, then yes. How are we on this? Make sense? Yeah, please.
If you're not accounting for covariance, what is the theory behind it? Like most people who hear on radio also get newspapers, or is it because my question is different? My question is like, would it be possible that the radio is something that is not statistically significant, but newspaper is?
Sure. I mean, this is I don't know, an example, right? It's a case study. Anything is possible.
Is that like the covariance situation? Like,
So, I mean, on this data set, the only possible, model is the one I'm showing you at the top. Right, so without changing the data, you cannot get a different regression. Like, obviously, if you change the data, you can get anything. But on this data as presented, you cannot get different coefficients for a linear model here.
But looking at these two things together, can we say something about, oh, maybe newspaper readers are often TV watchers and radio listeners?
Yes, so exactly. So then you start, reasoning about the mechanism. And you also start reasoning about, presumably here, like all of these ads happened about at the same time. Because otherwise, if there is, temporal separation, you can measure this in a different way that allows you to estimate the effects of one more robustly. But here, you have them all kind of together contributing to the outcome, and you're not sure which one contributed more. So, you have to model them jointly like this. And you notice that once you control for, one, the effect of the other one goes away.
So what you're saying is if you have a set of variables that you predict will have an impact on whatever you're measuring, the sensible thing to do is just run a regression with all of them, right?
Usually.
But didn't the Google paper do multiple regressions where they would remove some variables?
Yeah, so there's a lot of subtlety there that, some of this we will get into. Maybe the short of it is, all of these models make different assumptions. You make different assumptions about, different mechanisms. The types of models themselves maybe make different assumptions about the shape of the data, the nature of the relationship, the whatever. So, there's all kinds of subtlety that goes into this, which is usually why you see the better papers actually trying different models, right, with different specifications, with different types of assumptions, etc., to see how robust an effect is, right? So it's ultimately the difference between, did you just get lucky and you happen to stumble across one model specification for one type of model in which this one coefficient that you care about happens to be statistically significant? But if you actually, do some sensitivity analysis and robustness checks, it all goes away, meaning, you're cherry picking. Versus is this something that's, looks much more robust and robust to different assumptions about the whatever underlying distributions and modeling assumptions and so forth. So usually you see that, more care goes into this. I won't go into all of that today. We'll see a bit more of this throughout the semester.
So there is some value in doing, for instance, these tests on the left-hand side.
Yes. Like ultimately, remember, like it's not about the statistics. Like ultimately, what you want to do is reason about alternative explanations. It's like you use any means at your disposal to build that argument. Like these are pieces of evidence that you use to construct this argument. The outcome, the value, the prize is the argument. It's not so much the kind of, what stats you use. But your arguments will be more or less credible depending on what stats you use and how you set up the analysis and what assumptions you make and how you clean your data. And like we'll see actually a few good examples of all of this in a minute. But like, in principle, is there any value in exploring data? Absolutely, right? Always. But you should be cognizant of the assumptions you're making, basically, when you're doing that, and how strong the claims can be from that kind of evidence. Right. So here, the claim is not very strong if you do this in isolation, because we know that the other things co-vary by design. We know that they were buying ads on radio and TV at the same time as they were buying ads on newspapers. Right, so if you just analyze the effect of newspapers without considering that there were also, contamination from radio and TV ads, that's a little misleading, right? Because you happen to know more about the, the process that generated the data. Okay, all right. So then interaction effects, I think we saw some examples before, so I will go pretty quickly over this. All right, so right now we increase, let's say we're looking at beta 1. If we increase x1 by 1 unit, y will increase by an average of beta 1 units. No interaction. We can include an interaction term, meaning the product of these two variables. So that means that increasing changes in the second variable x2 will moderate, or the second variable x2 will moderate the effect of x1 on y, right? Because depending on the value of x2, the slope of the relationship between x1 and y will differ. Okay, so that's a definition of an interaction effect. And we've seen an example of this before. So here's more concretely, credit card balance as a function of income, which is a numeric variable. So that's, I don't know, your PhD stipend or income, and whether you're a student or not. Right? Maybe we have some, I don't know, non-students or something. So student is a categorical variable that, it's a flag that tells you if you're a student or not. Income is a number. So without an interaction term, then you're basically fitting two parallel lines to the data here, one for students and one for non-students, right? So the slope is the same for both of them, right? But the intercept, the value at which they start, is different. Right? So this is what it means to model these things without an interaction effect. Same slope, different intercept.
Which just means there's no interaction in between.
Yes, and this is a modeling choice. You could test for an interaction, right?
Between what?
Between being a student and income. Or income and being a student. So does income moderate the effect of being a student on credit card debt? Or similarly, does being a student moderate the effect of income on credit card debt? Right? So probably you would argue that there is such a mechanism, right? There is probably a moderation effect there. So you may want to model an interaction term. I will show you what that looks like in a second. But the point is, without an interaction term, what you end up modeling is just the fact that these lines are parallel but at different intercepts. They intercept the y-axis in different places. Right? So that should be clear from just the coefficients here.
The interactions between student and non-student? No.
No, between student and income. There is no interaction. This is a model that has two variables, has a numerical variable called income.
Makes sense.
And the estimated coefficient for that is beta 1. Has a categorical variable, a flag called student. The values for that are 1 or 0. The estimated coefficient for that is beta 2. Okay. So this is what you end up with. If you include an interaction term, which can be argued both ways, right? So, being a student moderates the effect of income on credit card debt, or vice versa. Income moderates the effect of being a student on credit card debt. You could read this either way. Then you also get different slopes between these. And we saw an example of this with typing speed and device that we went over, I think, in quite a bit of detail, I don't know, a couple of lectures ago. So hopefully this is not surprising. Okay, so now a few tricks here.
Can we pick up?
Yeah, of course, yeah.
So how did we explicitly add the interaction term?
Including the product of the two variables.
Or
So we still have income that give with beta 1. We have student by itself with beta 2. But we also have the product of income and student with beta 3.
I see, yeah.
That makes sense?
Yeah.
So that means that depending on the value of income, right, the effect of student will be greater or smaller, or vice versa, depending on how you want to read this.
Does this also apply to both variables and numerical? Does the, for instance, the parallel line thing without interaction effects, is still that the case in both variables and numerical?
I'm tempted to say no, but I need to scribble this.
What's the question?
If the parallel effect there was because this was a categorical variable, student was a categorical variable, would it still be parallel if it was a numerical variable?
It cannot be like a variable in the form it was written.
What I mean, yes, but if it's something else, like your parents' income, your income versus your parents' income or something, instead of student. Or your GPA is a numerical variable. So, not being a student, that variable is a categorical variable as we defined it, but it could be, if it was a different variable, it's what you're asking.
But if you could write it in a way where you're saying balance equal to something, if something, it will be categorical. If it's non-categorical, then by definition, you'll have to put it in the equation, and then you might not get the balance out.
So, I mean, look, not sure what you were arguing. Debt, beta 0, beta 1 times income, that's a number, plus beta 2 times GPA, H index. Right? Your credit card debt is a function of your income and your H index. So if this is a number and this is a number, then I guess they don't need to be parallel. Is that true? I think that's true. They are not, I think. Is that right?
They cannot be,
They cannot be.
because to be parallel, they would need to have just a constant value difference between them, which is not the case. Income is also
Which is not the case. Yeah. Yeah. So the parallel effect was an artifact of this being a categorical variable.
You like a
Good.
plane in the 3D, instead of
I don't follow.
I'm still trying to pass the parallel thing. Like, it could not be parallel because the H index will change, but we don't have H index here, right? It has to be a plane, so it's gonna be 3-dimensional. 2 dimension for income and H index, and third for balance.
But I mean, the relation between debt and income would always be in 2 dimensions. And between debt and H index will also always be in 2 dimensions.
Yes.
So the point is they cannot be parallel because they are related as an income.
I mean, they're not.
At a given H index, the value of at a given H index in debt, whatever the value of income is, will also determine the slope. So these two cannot be parallel.
Yes.
So this is how much debt changes for a unit's increase. Right? This is the slope of the relationship between debt and income. It's like this is the slope of the relationship between bet and H index.
I'm just saying that the x-axis is going to change, so putting them on the same graph does not even make sense. It's gonna be like, if I have to draw all of these things together, I need a 3D representation.
Okay, so then on this, yeah, there's a good point. Yes, there's a good point in here that I would like to get to. So let's see if I can. So let me continue, please.
I don't
Let me not
understand.
continue.
I don't understand how you just added the third term we did 3 times income to study the interaction.
How I added it, or why it captures the interaction?
Latter.
It captures the interaction between, because, so student is still there on the right. Okay. So the effect of student on balance, that's the first row and the second thing that is here. Over here. Okay. The effect of student on balance depends on income. Right? So it's not independent of income. You know, low
Yeah.
income would result in a different effect of student on balance than, say, high income.
And technically this model is better than the previous one.
I mean, that depends on the data and your theory and so forth. But this is an illustration of how you model an interaction effect and how you interpret it. And why this kind of product of these two variables in a regression model is equivalent to measuring the interaction between those two variables. Okay, so a few things that can go wrong. What if your data is non-linear? Right, we've assumed linear relationships so far. What if it's not linear? Right, what do? One thing you can do is, remember this plot of residuals that I started with earlier? You could look at that. You could see if your errors look like a cloud of noise, or if there's a pattern to your error term. Right? If there's a pattern to your error term, that probably means you have insufficiently captured the shape of that relationship. In this case, there's a clear, quadratic shape to the error term. So that would lead you to conclude that, a linear approximation was insufficient, which obviously you can tell directly. But you can't always tell this because, I don't know, the data is multi-dimensional. Right, so compare this to the residuals plot for the previous model, or rather previous sample that we modeled. Okay, so that's one. Now here's a cool thing, a gotcha moment. If you actually look at the two estimated regression models for these two data sets, they are identical. Okay, meaning the estimated coefficients and the fit of these models is identical between the two. And obviously that's by construction. This is an artificial example to prove this point. The point is that you cannot just, I guess to your point earlier, you cannot just run a regression and be done and assume everything is, valid or interpretable as is. You have to do all of this debugging and investigation to, you have to be skeptical, right, of what your regression is telling you. Okay, let me skip this one. Okay, another possible issue is error terms, well, I guess, related to the previous one, error terms that are correlated, especially with the longitudinal data. So this is some time series data. I'm showing 3 examples here of the error terms, the residuals. These are all artificial examples The first one is constructed assuming there's no correlation between the error terms at time t and error terms at adjacent time points. So you can see that it looks more or less randomly distributed around the 0 line, which is what you would like to see. In the lower ones, there's increasingly higher correlation between the error terms at adjacent time points. So then you see these clear patterns which tell you that something is probably going wrong with your model. Okay, there's this assumption of independence of observations when you're doing this kind of regression modeling. In this case, they are clearly not independent, right? Because the values at time t seem to depend quite strongly on values at time t minus 1, which violates one of the assumptions of being able to run this model in the first place. Okay, so I guess I didn't say anything about how you fix this, did I? Let's see if we can come back to that.
Was there an assumption that said something like that they cannot be correlated?
There's an assumption of independence, yes. There's a number of these assumptions. Yeah. One of which is that the observations are independent. So by the way, let's say tangent. Let's say you're modeling network data, which is something we've done a lot in in my group. You construct networks of people or whatever, dependency networks, whatever it may be, construct networks, and then do some analysis on variables computed over these networks, right? By construction, these variables, these observations of different nodes in the network are not independent of one another by definition, because they're observations of nodes in a network. So then, like, you're screwed. You can't, you can reliably use any of these methods because that sort of fundamentally breaks one of the assumptions of, these models in the first place. So that's a story for a different day, but, interesting, quirks of, I guess, the domain you're working in. Okay, another type of plot that you often look at to debug these models is residuals on the y versus fitted on the x. So residuals is the error terms. Fitted is the predictions your model makes at the same inputs. Okay? So you can see, for example, some kind of pattern. These also should not have any discernible pattern to them. You see some kind of pattern here. You see that there is increasing variance in the error terms as the value of the response increases, for instance. It doesn't have to be this shape, but this is just an example. So there's actually an easy fix, which is why I'm mentioning this. There's an easy fix for something like this, which is to just log transform your original variables to compress the ranges. So that will miraculously solve this problem for you. So that's a cool hack. Okay, so remember to always log your, I guess, counts.
I mean, how do we know the problem is resolved? Is this a data thing, like now that the residuals look back?
Yeah, that means problem is resolved. Residuals look random is a good thing, is what you hope for. That's the goal.
But now whatever you're fitting is on the log.
Correct. So the interpretation changes.
There has to be some exponential interpretation.
Excellent observation. That is correct. Right? Because it's not 1 unit increase in the original variable, it's 1 unit increase in the logged variable. Right? Which corresponds to a unit E, whatever, factor E increase in the actual variable. That is an excellent observation. Very good. Okay, this one is one of my favorites. There's this, I guess you cannot read it. It says outliers and high leverage points. Okay, so the example on the top left is an example of an outlier point. It's the one that's sticking out, right? It's kind of, off the trend line. That's an outlier that is not also a high leverage point, because should you remove it from your sample, the slope of the regression line would not change drastically. So yes, it is an outlier, but it's not a particularly harmful outlier or problematic. So maybe you don't need to remove it. The one on the right is both an outlier because it's, far from the mass, right? The center of mass of the distribution, but also a high leverage outlier, because should you remove it, the slope of the regression line would change drastically. In that case, the relationship is vertical, right? And depending on how far you add this point, you could turn it into, for example, completely horizontal, which would be very misleading. So, like, yes, outliers are dangerous when you're doing this kind of modeling, but not really, right? If they're well behaved, if they're outliers on the same trend lines, they're probably harmless. If they're high leverage outliers, you should do something. You should decide, right, what to do. Like, you should look at this and, use your domain expertise and say, is this a measurement error? Is this an artifact of something else? Is this something I should treat separately? Is this something I just remove because it is so atypical? And maybe I want to make a claim about, trends in my sample. Trends by definition means, stuff that's common for most, elements, items, people. So maybe that's okay to remove these outliers, right, for the purpose of that trend analysis. But this is a decision you have to make deliberately, because if you don't, right, the estimated coefficients, right, for this regression will be way off, depending on whether you include or you keep these high leverage outliers or remove them. Right? So this has to be a deliberate decision. You see what I mean? The slope of that estimated regression line would change drastically in the example on the right if you keep that outlier high leverage point in your sample compared to if you remove it. So you have to make this decision deliberately, right? Because you're concluding that you're interpreting that estimated coefficient, right? That describes the nature of the relationship between your X and Y variables. So that should be robust to, high leverage outliers. I'm seeing Rasoon.
Two questions. The one is, what if we have like more than one points, what we call as a high leverage group of points? Let's say I'm collecting multiple samples from every user in my study.
Yep.
And one of the users, all the points are somewhere on the outlier.
Yeah.
In that case, would the decision be to remove all of those points, because each of those points individually are not high leverage points?
This is how you end up in jail, basically, right? Remember the famous Harvard deception story? So they move some data points from the treatment group to the control group or vice versa, just because it aligned better with their conclusions. So, be careful with stuff like this. This is how you end up in scientific jail. I mean, so you have to make a decision, but just be careful with what you're doing, right? Because there's a fine line between data cleaning and denoising, and p hacking or whatever. Right?
I think the second thing that I ever had was related to this. Wouldn't the better theory be that we kind of study the characteristics of that user, and the entire theory should be more comprehensive?
So I agree. So you should do something. Like you cannot just, you cannot do something silently. That's for sure. Like whatever you do, you have to be transparent. And you probably should do something. If you remember in the meter paper, there was a really nice discussion where they said, turns out there was this one user who self-reported they had no experience using whatever AI tools, but turns out I don't know, they lied or whatever, they made a mistake. They actually had 50 plus hours of experience using the AI tools, right? So like that, that's a point that you move from one group to another, which could change your conclusions. And the way they handled this, I thought was great, right? They said, look, let's see how our conclusions would change. How robust are they to where this one point gets bucketed, right? This one user gets bucketed. So to your question, like you would do something like this, right? What happens if I decide to, exclude this user entirely because they're weird, right? Versus, include them, or versus do something
Yeah,
else, right?
that would be a more coherent version of, because right now, making a claim, especially in the second column, of that is what the regression line is, it doesn't seem.
But I mean, from their perspective, right? The user could just be like, like, how is it my fault that I don't know, program much faster than everyone else? Like, why should I be punished, right? For, why should you exclude me from your study if I just happen to be a better programmer, or, something like that, right? So, from their perspective, you're also maybe biasing your sample in an unfair way, right? By deciding to exclude them, for instance. I don't think there's a clear answer to this kind of question, is what I'm saying. I think, the best you can hope for is to test the sensitivity or the robustness of your conclusions to different decisions regarding this issue, and be very transparent about it in the paper, so you don't end up in, scientific jail. Okay, so I guess given the time, let me pause here. I was somehow overly optimistic about how far we were going to get with today's class, but thanks for asking lots of questions. I will continue this on Thursday. Please bring a device so we can do something hands-on.
Thank you.